All right, so now we're ready to look at chapter 9, which is inferring population means. Right? So remember, inferential statistics, I mentioned before, is the heart of statistics. Right? So now, before in chapter 8, we look at inferential statistics with population parameters. Now we want to do some inferring with population means. Right? So some chapter 9 topics, big topics we're going to look at, is be able to apply the central limit theorem for sample means, and then also be able to make inferences about population means using confidence intervals and hypothesis tests, right? So we're doing similar things in chapter 8, but with population means now. So section 9.1 kind of just sets the stage to start talking about those items. So section 9.1 is sample means of random samples. So some big picture things here is we want to be able to discuss the accuracy and precision of the sample mean as an estimate of the population mean, and be able to find the standard error of the sampling distribution of the sample mean, right? So there is some repetitive topics in this section. So the first part is looking at three characteristics of the sample mean, so looking at accuracy, precision, and the probability distribution. And also there's some notation review here. So remember, we use the Greek letter mu for the population mean, x bar for the sample mean, use sigma here for the population standard deviation, and S for the sample standard deviation, right? So you want to make sure that you're comfortable with that notation still. And to be able to remind ourselves what accuracy, precision, and probability distribution mean. We looked at this in, was it early chapter 8, I think? Alright, so the section that we talked earlier about accuracy and precision in was 7.2, right? So, just to remember, right, if something is accurate, does the method measure what is intended? Does it correctly estimate the, well, here we would have the population mean, right? And precise, if the method is repeated, the estimates are very consistent, right? Remember, we looked at some examples with golf balls, right? So if you need to, you can refresh yourself on those terms, but those terms apply here also, just with sample means, right? So going back to 9.1, right? So going to slide 5. So remember that the sample mean is unbiased when estimating the population mean on average. The sample mean is the same as the population mean, right? So on average, if my sample mean is the same as the population mean, then we're unbiased, right, when estimating the population mean. And then the precision of the sample mean is going to depend on the variability in the population, right? And remember, the bigger sample size we have, the bigger observations we collect, the more precise we can come, right? The more precise that the sample mean becomes, right? So my sampling distribution can be thought of as a distribution of all possible sample means. That would result from drawing repeated samples of a certain size from the population, right? So if we keep repeating this process, my sampling distribution will be all the different sample means. And also we want to remember that when we're talking about a sampling distribution, the standard deviation, we call that the standard error, right? So a little different term, but a similar idea, right? So on this next slide, it is important to note that as we increase the sample size, my standard error is going to decrease, right? So if I look at these pictures, here's for n, maybe make this a little bigger, right? So this is n equals 100. Here's n equals 400, and n equals 900, right? So that red line is the mean, right? So that looks to remain the same, right, in all cases. But as we increase the sample size, notice that my my results are closer and closer to the mean, right? So that means there's less standard error. There's not as much deviation, right, between the values, right? They're all very close related, right? So that's important to note, right? So that's what that means in pictures. And on the next slide, after looking at the equation for standard error, it makes sense that my standard error would decrease the larger n gets, right? Because this is the standard error of the estimate is equal to sigma divided by the square root of n, right? So as n gets bigger, right, my denominator gets bigger. So if I'm dividing by a larger number, then that value is going to get smaller, right? So we can think about it mathematically, algebraically also, that would happen also, right? So let me go zoom back out. Right? So for all populations, the sample mean, if based on a random sample, is unbiased when estimating the population mean, right? So in other words, the population mean is going to be equal to the mean that I would expect, right? But the standard error is going to be equal to sigma divided by the square root of n. So as the sample size increases, the sample mean becomes more precise, right? So here's an example. So we're told, given this scenario, a student has a large digital music library. The mean length of the songs is 258 seconds with a standard deviation of 87 seconds. The student creates a playlist that consists of 30 randomly selected songs. So part A, we're asked, is the mean value of 258 seconds a parameter or a statistic? We want to explain, right? So let's do one question at a time, right? So if you go to slide 11, you can see the answer for A. So we're asked, is the mean value of 258 seconds a parameter or a statistic? Explain. So if I go here, the mean value of 258 seconds is a parameter here because it's the mean of the population, right? All songs in the digital music library. That's what we're considering the population. So since that's the mean value of all of the songs, that is a parameter, right? Remember P and P. Parameter goes with population. Statistic goes with sample, right? S and S. Those match. All right. So part B of this example. What should the student expect the average song length to be for his playlist, right? So what should we expect to be the average song length? So if I go back to slide 11, part B is the answer, right? The student should expect that the average song length of the playlist is 258 seconds, right? So the sample mean is typically the same as the population mean, right? So that's typically true, right? If we're unbiased. So then slide 10 has two more questions. Part C. What is the standard error for the mean song length of 30 randomly selected songs, right? So the last slide, slide 12, has that answer. And we just need to plug it into our equation, right? So we have sigma divided by the square root of n. So we were given that the standard deviation is 87 seconds, right? That's sigma. And we were creating a playlist of 30 randomly selected songs, so n is 30, right? So if I plug that in, I get 15.88 seconds, right, as my standard error. And then part D says, would a playlist of 50 songs have a standard error that is greater or less than your answer to part C? Explain, right? So if the playlist had 50 songs, that's bigger than 30 songs. So remember, as my sample size gets bigger, the standard error gets smaller, right? So the standard error decreases as the sample size increases, right? So the answer to part D is we would expect the standard error to be smaller, right? So larger sample, smaller standard error, right? All right. So make sure you're watching the videos and doing the homework. We have just a few sections left, right, in chapter 9, right? So remember also when doing chapter 9, these are the main things to focus on, right? We want to be able to apply central limit theorem for sample means and also be able to make inferences about population means using confidence intervals and hypothesis tests, right? So using both, right? All right, so now we kind of set the stage and we'll continue on with these items.